Hello friends, welcome to another tutorial in wave propagation series. In this tutorial we'll take our discussion to the next level for ionospheric propagation. Another name given for ionospheric propagation is sky wave propagation, and this type of propagation is very suitable for waves of the frequencies from 2 to 30 megahertz. So if we were to define what is ionospheric propagation, we can define it as the propagation of radio signals where we send the signal through ionosphere and it comes back to the earth after reflection, and that reflection occurs because of subsequent refractions, and we'll talk about that in a minute. So I highly suggest that you watch my previous video where I talk about the layers of ionosphere, how are different layers formed, and what are the various ionization densities of different layers, because that is going to play a very important part in this video. So in order to understand how a radio signal takes a path through ionosphere, we need to know a few key points. The first key point is the Snell's law. It says that if we go from, let us say, denser to rarer medium, a wave goes from denser to rarer medium, so it bends away from the normal. So you need to take care of this law. You need to be aware of this law, that when we go from denser to rarer medium, if we send a wave at some angle, it'll deviate away from the normal, and the reverse of that is true also. If we go from rarer to denser, it'll bend towards normal. And the second key point is that the ionosphere's refractive index eta decreases as we go up. So what happens is the layer, the lowermost layer has the highest eta. It is the densest. Then we have less dense, and then we have even less dense, and then finally we have the rarest at the top. So what do we expect when we go from one layer to the other? Will bend a little away from the normal. So that is what is expected, and at some point that refraction will be translated into total internal reflection, and that is what causes the wave to turn back to the earth. So let's see how that happens. Now, in order to understand, I've drawn this illustrative diagram. Over here I've not mentioned the names of the layers to be D, E, E, F1, F2. Instead, generalization of the layer is happening, and we know that the eta of this layer will be dense and more, rather eta will be more of N1. It will be denser and then rarer and rarer as we move up. And what's the reason behind that? What causes this ionospheric bending? Let's see that. So you need to remember this very important formula. We know that the refractive index eta is dependent upon the ionization density, and the formula of relation is this: eta is equal to under root of 1 minus 81 n upon f square, where n is ionization density and f is the frequency with which we transmit the signal. For example, I'm talking about a frequency of 2 megahertz, so it'll be this eta will be different for that wave, and eta will be different for a wave of higher frequency. So that being said, we know that the n for the layer number 1 will be the lowest, and n increases as we go up in altitude, because n is ionization density, and at higher levels the ionization is more. So that is how it is represented, that ionization density for 4 is greater than that of the 3 and that of the 2 and that of the 1. So an inverse relation occurs for the refractive index. Eta 1 will be greater than eta 2, will be greater than eta 3, and will be greater than eta 4. So n increases as we go up. That's the key point. Must remember. And eta decreases as we go up. Right? So when that happens, if we transmit a wave at certain angle, when it encounters the first boundary, we consider, let us say this is the D layer, so we go from denser to rarer and it bends away from the normal. Some refraction occurs and it is bending away from the normal because it is going from denser to rarer. And again, this phenomena happens denser to rarer, and there comes a point when total internal reflection occurs. And we see that while we come back in the reverse path, it again moves towards the normal, which is expected as we go from rarer to denser. So we are moving towards normal, so that will facilitate us, and finally that will help us in returning of the wave to the receiver. How can we calculate this distance and so on and so forth? What is the cutoff frequency and what is the all those things are to be calculated later on, but that's the essence of ionospheric propagation. The essence of ionospheric propagation is the ionospheric bending, and that bending happens with gradual refraction happening at every layer, and finally the refraction happens so much that it leads to a total internal reflection, and that causes the total bending. So I hope this concept was clear. These formulas were very important, so I wanted to mention these formulas, and that's about it for today's tutorial. And I hope you liked this short video. If you did, give it a thumbs up, consider subscribing to the channel. I'll see you around in the next video to come. Till then, take good care of your health and stay happy. Bye bye.